last class what we did was that we showed that what the similarity transformation was and how it can predict the right result, right. At the same time we showed that the scaling was able to predict the correct variation. Okay. Now we also suggested in that particular lecture that if it is just the value of the gradient at the wall, be it temperature, be it velocity, that is all that we need for evaluating what will be the heat transfer coefficient and the skin friction. Why resort to all these things? Let us devise something which is a little bit more simpler, right, and that is how we suggested that maybe we can have a semi analytical type of an approach. Okay. So, based on this we move to something called the integral solution. Okay. So, this was like von Karman and Paulhausen. Okay. So, the main building block of this particular approach is assume a velocity profile, okay, which is not exact because we do not know without the actual solution what the velocity profile would look like. Okay. So, assume a velocity profile for u and t basically, right, okay, inside the boundary layer, thermal or otherwise. Okay. And because this should work, because all we need to kind of be concerned are variables like these, right, at wall, right, that is our main concern. So, why not assume something for u, something for t, such that, so that means if the profile is like this, right, the normal boundary layer is like that, correct, that is what we drew. So, if I can draw an inexact profile, something like that, okay, which kind of resembles this, okay, but it does not quite, it is not exact because we do not know the form. But if this boundary profile, whatever is the assumed profile, so to say, should obey all the boundary conditions, right. Okay. So, I cannot have a profile which is like this, say for example, okay, that will not be physical, okay, that will not, for example, agree with the boundary conditions either. So, one is that it should obey all the boundary conditions, and the second thing is that it has to be physical in the sense that it has to obey certain physical characteristics. Like for example, this profile that I drew over here, this curved kind of a wiggly pattern, right, you know that this profile is not physical, because why a profile should be like that, right, because the high velocity, low velocity, it cannot exist in a steady flow like this, okay, which is laminar in nature, correct. There is no mechanism by which why this should happen. So, even though this profile might satisfy the boundary conditions, this is not a physical profile. Okay. So, let us take this more carefully because I want you guys to get the, so this is the actual profile. Say for example, I draw a profile like this which kind of agrees with the boundary condition here, with the boundary condition there, correct, but in between it has got all these wiggles. Okay. So, this is not allowed, this is not allowed, okay, since it is not physical, right. That is the most important part, that it has to make common sense, right, and there is no mechanism through which this flow will make something like this, okay, even though the boundaries are still satisfied. Okay. So, these are the two prime parameters that we need to get a feel of. One is that it has to obey the boundary conditions, second is that it has to obey the physics. Okay. Let us look at, before we do this, let us put down one particular form, okay, which is called the Leibniz formula. Okay. So, Leibniz formula for differentiation of an integral with respect to a parameter, okay, with respect to a parameter. Okay. Okay. So, we change the pen color to something like this. Okay. So, let us take this particular form, and this will come in very handy. This is the generalized form. Okay. So, pay attention to the details. Okay. So, that is the form. That is the first one, plus minus that is the Leibniz formula. So, you can see that how this will come in handy, we will see in a second, but this is the form of the Leibniz formula. Okay. Now, we are going to need this when we actually do this integral formulation. Okay. Now, let us take the case of a, let us go back to our problem, let us take the case of a flat plate. Okay. It can be a wedge also. The wedge part we will do the similarity a little later. Okay. So, flat plate will be like this, wedge will be something like that. That means an inclined flat plate, okay, whatever it is. Okay. So, let us take that particular form and let us try to work out the equations. Okay. So, this is the standard, this is the flow u infinity t infinity, this is x and y, this is the corresponding delta. The thermal analysis we will go a little later. Okay. So, the continuity equation is du dx plus dv dy is equal to 0, this is 1. Okay. The x momentum is du dx plus v du dy . I will tell you the origin of the last term, this is 2. Okay. This origin of the last term is comes basically from the pressure gradient, right. This is basically nothing, comes from the Euler's equation, correct, outside the boundary layer. So, for a flat plate this is equal to 0, right, for a flat plate it is equal to 0 for flat plate, but when you are dealing with a plate which is inclined, okay, this will not be equal to 0. Right. So, this is basically the variation of the free stream velocity with x, that is all that is, right, and that comes from the Euler's form. Okay. So, the boundary conditions we already know, y equal to 0, u equal to 0, v can be equal to 0, it can be also equal to some other quantity which is called blowing or suction. We will cover this a little later, but it is like if this plate is kind of porous, okay, that means there is a flow coming up like this, that can be accounted for by Vw, okay, or if the flow is porous and the fluid is actually seeping through, okay, so that can be given as Vw. Okay. So, it is normally will be 0 for impervious plate. We will do all these special cases later, I am just writing it in a common way, so that later on we can use we do not have to come back to the integral formulations once again. Okay. But most of these terms are 0, as I said, this is 0, this is also equal to 0. Okay. But there are special conditions, as I said, that in some cases there can be a flow, that is suction or blowing, right, or there can be this flow outside the boundary layer may actually vary. Okay. So, now what we do is that we take the continuity equation and we integrate it with respect to x. Oh, sorry, with respect to y, okay, because that is the y variation we are trying to take out. So, du dx dy plus 0 to delta dv dy into dy is equal to 0, right. Okay. So, that is the form that we have. This leads to 0 to delta du dx dy plus v delta minus v0 is equal to 0. Very simple, right? That is the form. Now, we are going to apply Leibniz rule on this. Okay, we already established the Leibniz rule. Now, we are going to apply it first to our continuity equation. Okay. So, by Leibniz rule, this will be du dx dy will be u dy minus u at delta d delta by dx plus u0 d0 dx, right. Okay. That is the lower boundary, 0 is basically the lower boundary, right. So, this gives you du by dx 0 to delta u dy minus u infinity d delta by dx. Of course, this goes down to 0, the second the third term. Okay. So, therefore, now combining the full continuity equation, therefore, that is the full form that you get. Okay. Now, of course, v equal to v at 0, you can put whatever values that you want, v at delta you can put whatever values you want, okay, and all these things are incorporated. This is the most generic form of the equation that we can write, got it. Okay. So, now that we have taken care of continuity, let us move on to the momentum. Let us write the momentum equation in a conservative form. This basically goes to 0. I am putting the whole thing so that it is easier for one to understand that how we are proceeding throughout the problem, right. So, that is the whole form of the equation. Now, again integrate with respect to y. So, this will come as this. Got it? That is the full form. Okay. Now, again you can apply your Leibniz. Okay. I am not going to go through the steps, but you can apply your Leibniz accordingly. Okay. So, the form that you are going to get after Leibniz . Okay. Right, the full version of this full equation. Okay. So, you can see a few things over here, okay, which we can eliminate, okay, and some of those things should be pretty common sense as well, that what are the parameters that we can eliminate. Okay. So, let us see that which are the parameters that we can safely eliminate. Okay. If you take your pick, say for example, few things to note, what is u square at delta? That must be u infinity square, right. U at delta is actually equal to u infinity square, right. Similarly, this particular parameter obviously will go to 0, we know that for sure, right. U v, whatever is the nature of v, even if there is suction or blowing, u is equal to 0 always. So, that should go to 0 at the same time. Of course, this parameter will stay depending on what you want your u v to be, okay, and or will it stay, we will see to that in a little bit. Okay. And of course, on the other hand, if you go to this side of the equation, you will find that what about the nature of for this, should this go to 0 as well, because you are looking at the shear stress at the edge of the boundary layer, right, where the flow, the velocity should have actually become equal to u infinity. Okay. All that gradient is very small, that is what we are arguing. So, so therefore, we can write this equation in a more nicer form. This part remains the same, plus u infinity, if you take the u infinity, v is equal to actually u infinity. Okay. So, this is will be given as v 0 plus u infinity d infinity dx, okay, and d infinity dx minus d dy is equal to u infinity delta into du infinity by dx, okay, minus gamma du dy evaluated at 0, right. So, that is the total expression that we get. Okay. So, now doing some more algebra, taking u infinity square out, 0 to delta u by u infinity square dy minus d by dx square 0 to delta u by u infinity dy is equal to minus u infinity, okay, minus v u infinity. This is whatever that Vw was, suction, blowing, it can be 0 also, okay, suction, blowing or 0. So, that is what we are arguing over here, okay, plus u infinity delta du infinity by dx minus tau wall by rho, okay, minus tau wall by rho. Okay. So, that would be the other part of that term. Okay. So, the tau wall minus rho is basically nothing but du by dy evaluated at the wall, right. So, this is the total expression that you get, okay, and simplify this by a little bit, 0 infinity u by u infinity dy plus got it. Now, so this is the total form of this equation. Now, in many cases you will find that this will go to 0, this will go to 0. So, that will be the form that we will be left with, okay, in the absence of any suction and blowing or in the absence of any free stream variation in the free stream velocity, right. Now, based on this we can define basically two parameters, one is called delta 1, which is basically this dy, this is has got a name, it is called the displacement thickness, may have heard about it in your fluid mechanics course, right. So, this is displacement thickness. The other one is basically what we call the momentum thickness. Okay. So, the displacement thickness and the momentum thickness. Okay. So, these are two parameters, one basically represents this, one basically represents that, right. Okay. Now, putting these two terms in, this is the global equation. Got it? So, this is the global equation, right. So, we have reduced the differential equation to an integral form. So far this particular equation is exact, there is no problem, okay. We have not assumed anything. So, if you take a differential equation, you can arrive at this form without much of an assumption. Whatever is the boundary layer assumption, that is still valid, except that we have not assumed any velocity profile as of now. Now we are going to do that. Okay. So, let us assume a polynomial velocity profile. Okay. Why a polynomial velocity profile? Because it should be able to satisfy the boundary conditions that are at hand, and a polynomial kind of can represent, okay, without any kink, the boundary layer velocity profile, right. So, it can be other profiles also, by the way, so long as it makes physical sense. So, this is a common polynomial profile ABCD, okay, typical third order polynomial. Okay. So, y is equal to 0 at u equal to 0, right, and y at y equal to delta u is equal to u infinity, at y equal to delta du by dy is equal to 0, right. These things we know, right, we already know these parameter space. Okay. So, if we now try to put at y equal to 0 what happens, and for a flat plate, before we go to that, for a flat plate, this this equation gets revised a little bit, because your V w is equal to 0 and du by dx is equal to 0 also, right, flat impervious plate, right. So, for these two plates, this is added assumption can be done. Okay. So, now the point is very simple. Let us now derive that what will be the values of these coefficients, because that is what we need to plug in, right. Okay. We need to plug in over there. Okay. So, we need a fourth boundary condition, because there is A, B, C, D, right. So, we need one more boundary condition over here for V. So, for that particular case, at y equal to 0, you are assuming that d square u dy square is equal to 0. This is called a derived boundary condition. Okay. So, based on this, let us work out the profile. So, from u equal to 0 leads to a equal to 0, right. U delta equal to u infinity leads to a plus b delta, of course a is being equal to 0, plus c delta square plus d delta cube, okay, d delta cube, that is u infinity, right, du by dy at delta is equal to 0, okay. So, that would imply b plus 2c delta plus 3d delta square is equal to 0. Thirdly, dy square, okay, at 0 is equal to 0 implies 2c is equal to 0. Okay. So, based on all these things, accumulating all these parameters, okay, we have u infinity is equal to b delta plus d delta cube, okay, got it, and the other one is 0 equal to b plus 3d delta square, right. Okay. So, you can solve for b and delta from these expressions. So, therefore, u by u infinity becomes 3 by 2 y by delta minus half y by delta cube. The velocity profile that we get, assuming that this is the parent equation. We have taken care of two of the terms, and this is the velocity profile that we have assumed, right. So, this is approximate, this is not approximate, that is exact. Okay. So, this is approximate and this is the velocity profile that we get, got it. Okay. So, for no suction and blowing particular case and for a flat plate, this is the equation. So, therefore, if we write tau wall by rho, that will be the form, right, of the expression. So, now if we put this thing together, this is basically what we wrote earlier, remember, u by u infinity dy plus du dy at y equal to 0. So, now you plug in all the parameters, as u infinity square 0 to delta 3 by 2 y over delta minus half y by delta cube, that is the first term. The second term is 1 minus 3 by 2 y over delta plus half y by delta cube, right, okay, into dy, that is equal to 3 by 2 u infinity by delta, right. So, now it becomes du by dx u infinity square 39 delta by 280 is equal to 3 gamma u infinity by 2 delta, or d delta square by dx equal to 280 by 13 gamma by u infinity, right. Okay. So, now it is very easy because delta only depends on x, that we already know. Okay. So, in this particular case, if you do this, you will get delta by x equal to 4.64 into Reynolds number x to the power of minus half. Cf will be given by tau wall by rho u infinity square, right. So, you see that by using this simple enough expression, okay, we have got this result, which is 4.64, right. Remember, the exact solution gave us something like 5.2 if you recall the graph. So, we are not way off, we are off by about 10% or below in this particular case, right. So, that is what we get. Okay. So, just by using this approximate analysis, we got an answer which is pretty close to the actual value. So, this proves that the integral approximation is not a bad idea after all. Okay. So, based on this, what we have shown that your delta, you have to, after doing all these things, all we need is ultimately that expression for delta, right. Once we determine delta, everything, right, Cf and everything are basically dependent on delta, right. So, that is the thing that we have found out. Next class, we are going to go and do the integral formulation for the energy equation. Thank you. Thickness comes out to be almost the same as what we got through our normal similarity transformation. The variations are obviously the same. So, in this particular class, what we are going to do, we are going to look at the integral form of the energy equation. That is what we are going to do here. Okay. So, once again, as we know that there are two forms. So, these are the two profiles, one can be delta, one can be this. So, we are assuming that this is delta, this is delta t, and the wall is t wall, okay, this is t infinity. Okay. So, our basic assumption is that delta is greater than delta t, okay, which is usually the case as we said, except in liquid metals and other things. This is mostly the common type of fluids will actually follow this kind of a profile, right. Okay. So, delta is greater than delta t. Okay. So, u dt dx plus v dt dy, that was the expression that we initially had, right. So, t as y tends to infinity is basically t infinity, t at y equal to 0 is Tw, right, that is the wall temperature. Okay. Once again let us write it in a conservative form. Okay. Got it. So, now let us integrate. Got it. So, this was the conservative form of the energy equation, that means you include the continuity, okay, and this is we are integrating it with respect to y once again, that is what we did earlier. So, once that is done, okay. So, this is equal to 0, right, which is basically true because at 0 now we are not considering suction and blowing, we have already written. If you want to write it in a proper form, that can also be done. Okay. So, you can still continue in that particular way, but here V is equal to 0. So, that is what we have taken. Okay. So, this is also equal to 0 for the same reason, because the thermal gradient disappears as we move to the free stream, right. So, this is basically no blowing and this is basically the free stream, right, free stream, the gradient vanishes, right. So, these were obvious to you. So, now what we can do is that we can now write this particular expression, the revised form of the equation now as got it. That is a revised expression, right. Of course, looking at the nature of this particular term V t delta t and t delta t, we need to find out what this term is all about, right, that is what that term is. So, for that we would need to use the continuity equation, right, we can use the continuity equation for this. Right. So, V delta t is basically given as 0 to delta t du dx into dy, right. So, that is the V delta, because we needed that expression which you can substitute it there, right. Okay. Of course, T delta T you already know what T delta T is going to be, correct. Okay. So, if you do the so now that you have got this particular expression ironed out, okay. Now, how to proceed to the problem? So, this particular expression you remember that this is given, that the velocity at the edge of thermal boundary there, right, that is what it is, correct. Okay. So, now okay, so to we can once again apply the Leibniz rule over here to this particular guy. Okay. If we do that, then what we get is V delta t will be given by d by dx 0 to delta t u dy minus u delta t d delta t by dx, right. Okay. So, now we take this value of V delta t and substitute it here, right. we have to substitute it there. So, let us look at once after substitution what happens. So, the first term remains the same, plus t infinity minus d by dx y equal to 0, right. Okay. So, let us take term by term, so that we can, it makes a lot of sense to do the math properly. The first term, let us do that. Okay. So, the first term can be written as, again applying Leibniz. So, that you can see how the Leibniz is coming in handy, right. So, applying Leibniz we can get this, and not writing the 0 boundary condition anymore, which was a part of Leibniz, because you already know that that is going to be 0. So, that is the first term that we get. Okay. This particular term, so that was this term only, this particular term now can be written as, that is the second term of the series, right, can be written as d by dx 0 to delta t u t infinity dy minus 0 to delta t u dy dt infinity by dx, right. So, that is also that the second term that we are actually writing over there. Okay. So, now that we have finished writing these two terms, okay, now let us kind of assemble things a little together, okay, because we have all these terms spread all around. Assembling, you should practice this algebra in your leisure time, just so that you know. This is basically algebra, this is not much of a complicated math either. Right. So, that is the total temperature profile that you get. Okay. Choose these are the boundary conditions. Okay. And similar to the velocity boundary condition, right. So, similar to all these boundary conditions we get this also. So, choosing the temperature profile, then putting in the boundary conditions, we get this. So, if you now go through the math by putting in all these boundary conditions, I've already shown it for the velocity boundary layer, there is no reason to show it once again, reiterate it once again for the temperature boundary layer, that how you actually find them, right. But you can readily see, depending on our boundary conditions, this is the T wall temperature 1 minus 3 by 2 y by delta t, very similar to the velocity boundary layer, except that it is a 1 minus because of the opposite nature of the slope, right. So, that is what you get, right, if you plug in all the numbers, right. Okay. Now, if delta is equal to delta t, okay, the velocity solution is valid within the thermal boundary layer, right, is valid within the thermal boundary layer. That was the assumption that we made initially also, okay, because it is a thick velocity boundary layer. So, whatever the velocity solution was is kind of imposed on this as well. Okay. So, what we need to do now is that we need to pass on this temperature profile, okay, inside the full temperature that we got here. Let's call this equation A, right. That is where we need to substitute, okay. and we already have the velocity expression ironed out, right, because your u was already kind of known, right. So, it is not very difficult to do this. Okay. So, we are not going to go through the whole math steps for that. We can just write down some of the expressions that we have. Okay. So, if you evaluate all these integrals and other things, okay, what you will get is as follows: d by dx, okay, u infinity delta t delta, let us put a bracket here, or let us make this bracket okay, so that this can become now a third bracket. Okay. So, this is delta t by delta square minus 3 by 220 delta t by delta to the power of 4. Okay. Close this bracket is equal to 3 by 2 alpha by delta t. That is all that you get. Okay. Okay. So, that is all that you get after you substitute these expressions and if you evaluate. So, basically you have to put in u by u infinity that we already found out and this particular guy over here to the previous expression, and you just need to go through the motion. Now, of course, here there is a problem because we have now two variables delta t and delta, okay, to make things a little bit more dicey, right. So, in order to avoid that, okay, we already know that delta is greater than delta t. So, it is very natural if you compare these two expressions, for example, right, which is delta t by delta, we know that the fourth order term will be much lower, right, than this. This is 3 by 20, that is 3 by 280. So, there is a one order difference right there, right, and on the top of that this is squared, this is to the power of 4. So, naturally there will be more such variations over there. So, you can safely assume that 3 by 220 delta t by delta, okay, delta t by delta is much lower than delta t by delta to the power of 4 is much lower than 3 by 20 delta t to the power of delta square. Okay. So, that is already an assumption based on the fact that delta is greater than delta t. So, based on that, okay, so this simplifies, equation simplifies. 10 alpha over delta t is equal to u infinity d by dx delta t by delta square close bracket. We already know that delta is given by 280 by 13 gamma x by u infinity, that comes from your velocity or / momentum analysis that we did. Okay. Okay. And of course, the other boundary condition is that delta t at x equal to 0 is equal to 0. So, that is the starting point. So, the solution of this particular expression becomes delta t by x is 4.528 into Prandtl number to the power of 1/3 Reynolds number to the power of x to the power of half. Okay. So, that is the expression that we get, okay, delta t by delta. Now, we already know Nusselt number is defined as hx by k and h is defined as k. Just to recap, dy equal to 0 divided by Ts minus or T wall minus T infinity, not Ts, right, that we already knew, right. So, now it becomes a very simple thing that Hx then becomes 3 by 2 k by delta t, right. Okay. So, our Hx becomes 0.331 into k into x, okay, Prandtl number to the power of 1/3 Reynolds number to the power of x to the power of half, right, and Nusselt number becomes 0.331, it is the same, remains the same, Prandtl number to the power of 1/3, Reynolds number to the power of half, right. Okay. So, so this is actually very close to the error is actually less than 2.4%, the error less than 2.4%. So, you can imagine that it is a very robust way. So, all we have done is that we have got this expression, okay, and then we just substituted for delta, okay, and then we just integrated the whole thing, okay, which gave us this particular form, which preserves once again that Prandtl number to the power of 1/3, Reynolds number to the power of half dependence, and factor sits in front. The error is less than 2.4% compared to the similarity, right. So, I think it is a very powerful tool, as you can see, without doing much of a thing, okay, we are able to get this perfectly fine result, right, using just this kind of analysis. Okay. Now, we did for the constant wall temperature. We can also do the same for the constant wall heat flux. Okay. I am not going to do the full thing, but what I am going to do is that I am going to pose the whole thing, and it will be left up to the students to follow it up in the form of an exercise. Okay. So, uniform heat flux, that would mean that it is the same plate, okay, the same type of boundary layer is growing, except that instead of a temperature, fixed temperature, you constantly give a constant heat flux Q. Okay. So, that means you have put it, say for example, on an on a heater, okay, and the heater is connected to a power supply which supplies a constant heat. The previous case, you can consider it more to be you are placing it in an isothermal bath, right. So, that you have keeping the plate, no matter what, the temperature is always kept at a constant level, right. So, that it is always in equilibrium with each other. Okay. So, so this is how you are transferring the heat. Okay. It can be anything, it can be Qs double prime, say for example is the heat. Okay. So, once again the integral formulation, once you write it, that does not have any such problem, right. So, you can easily write the same thing in the same way that you did earlier, 0 to delta t u t minus t infinity dy, right, that is what you wrote earlier, dt by dy evaluated at y equal to 0, right. This expression still remains the same, there is no problem with this. Okay. Your velocity profile also remains the same. So, I am giving you the hints, the velocity profile still remains by delta minus half y over delta cube, right, all this thing remains the same, got it. Okay. Only the expression for h now has to be recast in a certain way. So, instead of that we are writing it in this particular form, wall minus T infinity, and Nusselt number is Qs double prime into x divided by k T wall minus T infinity, right. So, these are the two expressions, slight change because of the constant heat flux condition. Okay. You can once again assume the temperature to be the same, B0 plus B1. If you do not want to write it in ABCD, you can write it in this way also. Y cube, etc. Okay. The boundary conditions now are k dt by dy at y equal to 0 is equal to Qs double prime, the first boundary condition. Second boundary condition is at any x and delta t, it is equal to T infinity, which is also not difficult to, once again dt by dy, okay, at y equal to delta t is equal to 0, and d square t by dy square at y equal to 0 is equal to 0, right. So, these are the boundary conditions, the 4 boundary conditions that we have. Okay. So, applying, so what you need to do is follow the motions after this, that you need to apply the boundary conditions to find out what the temperature profile is going to look like. Once you get the temperature profile, it can be easily substituted now into this T minus T infinity expression, and you can find it. So, I will just give you the temperature profile finally before we wrap up. Okay. So, what we can see over there is that if you substitute all these things, the temperature profile will look T infinity plus 2/3 delta T minus y plus 1/3 y cube by delta T square Qs double prime by K. That is the expression that we get. Okay. Now, surface set, if you put y equal to 0, the T wall temperature becomes, okay, T infinity plus 2/3 Qs double prime by K into delta T. Okay. This is the wall temperature. If you put y equal to 0 here, you will get this, right. So, based on these two expressions, okay, now you are in a position, right, because your wall is now taken care of, okay, you know what is your wall temperature going to be. Now, you have to you have to do is to substitute this expression in the parent equation and try to see that what will be the final number, right. So, the final expression, if you manage to do this properly, will be 3.594 Prandtl number 1/3, Reynolds number half. So, the coefficients do change a little bit, okay, the coefficients do change a little bit, but this variation still remains the same. This of course remains is a different number now, right. So, that is your delta. So, that means when you invert it, you are going to get a different expression, a lower expression for your Nusselt number, right. So, based on this, your Nusselt number should be, if you do it properly, it is going to be 0.417, that is a higher value. Okay. So, Reynolds number to the power of half. Yeah. So, the Nusselt number will be a little higher because this coefficient is a little lower. Okay. So, that is the reason why you should have your Nusselt number a little higher. Okay. So, what we have done, we have shown that for the two sets of conditions, constant wall temperature and constant wall heat flux, okay, it is possible to cast the expression in a very similar way, right. So, let us just recap what we just did. Let us take the momentum equation. What we have done is that we saw the momentum equation, right. What we did is that we integrated out the y variation completely, okay, using Leibniz rule and using the pre-existing boundary conditions. We integrated out the whole thing, right. As soon as we are able to integrate out the whole thing, okay, we got an expression which has only depended on x, right. So, there we substituted and solved, we assumed a velocity profile, okay, a velocity profile which depends on y, and then once we did the integration, okay, we found that what will be the delta, okay, that means the boundary layer thickness. Once we knew delta, Cf and all the other parameters, we can determine it very easily. Now, coming back to the temperature profile, a basic assumption is that whether is delta is more than delta T, which is the most common type of fluid that we see, that delta is more than delta T. Using that expression, okay, what we did, we started with the energy equation, substituted the velocity, assumed a profile for temperature, again integrated the whole thing out, and finally found out how delta T varies with respect to x. And once delta T is known, as we know, the H, the heat transfer coefficient, is inversely proportional to delta T. So, we were able to knock out the heat transfer coefficient, and Nusselt number is nothing but the heat transfer coefficient minus the, it is a non-dimensional number. So, we got the correct expression for that too. Okay. So, it is a very simplistic approach by which we have assumed, central piece is that we have assumed polynomial for both velocity as well as for temperature, right. And this polynomial made sense because we were able to satisfy all the boundary conditions. In fact, that is how we found out the coefficients of the polynomial, and we found that the results that we got varied by less than 5%, right, with the actual similarity transformation, which was very difficult, which involved a lot of math and other things. This is a very simple integration, just a straightforward integration. Okay. Substitute the values of the y, that means the variation with y, integrate out with respect to y, and you get an expression which is a function of x only. Okay. So, in the next class, what we are going to do, we are going to look at some of the special cases which we alluded here, that there can be suction and blowing, there can be something called a wedge, which seems to be a little different from what the flat plate boundary layer is. So, we kind of just touched upon that. Next class, what we are going to do, we are going to look at the general case of suction and blowing, And after that, we are going to look at a new class of solutions which is called Faulkner scan, which is basically valid for these wedges, okay, those wedge inclined plates and things like that, where the free stream velocity is a function of x. So that means there will be a pressure gradient within the boundary layer. Okay, so see you next class. In this particular class, we are going to do something which is a general case of suction and blowing. Now, suction and blowing in this particular case, see, all the time in the previous classes also we said that what if there is a if the plate is not impervious in nature, that means you have this plate and it can either bleed like this, like a perspiration, or there can be a reverse direction of the flow. That means it could be porous and you could have this flow going down like that. Okay. So, for example, if this velocity is upward, we can say it is positive, and v downward we can consider that to be negative, right. So, so this is the general case of basically what we call suction and blowing, right, the mechanism of suction and mechanism of blowing. Now, how to analyze a situation like this, that is the thing that we are going to attempt in this particular class. Okay. So, here we are going to do a thing which you we will go into the details a little later, that we are going to take a generalized equation, and that equation will be valid not for just this plate, it can be also valid for a wedge. That means if the plate is at an inclined angle and if it is still blowing in the same way. Okay. But in any case, this part, that means the wedge part, we will devote a full lecture on it and show that how this wedge can actually affect the what will be the dynamics. Okay. But in this particular case, it's a general wedge. Okay, it's a general wedge that we have taken over here. Okay. And the equations that I am going to write, some of the equations we are going to derive a little later, but for the time being, for this particular class, you are going to take the equation as is. In the later lectures, you will understand how those equations are kind of applicable, what is the level of applicability. So basically this one and the general case of a wedge solution will come hand in hand. So you should ideally look at it in a more integrated kind of a fashion. Okay. So for a general wedge, because then we do not have to come back and again do it for a general wedge. Okay. So for a general wedge, the u infinity can be written as x to the power of m. Now, how is it exactly written? We will come to that in the next lecture. Okay. And it also has a uniform, say, surface temperature. Temperature T naught. Got it? So, it is a general wedge in which you have u infinity given by c x to the power of m. What m is, we will see. Okay. M is related to the slope, okay, of the wedge. How those things are related, we will come a little later, where the significance of m will be clear. For the time being, you can say that m is some way associated with this wedge angle. If that wedge angle is beta, m in some way is related to that beta. That is for the given at that. So it is a function of the wedge angle in some way. Okay. What those angles are, we will come a little later. Okay. But let us concentrate and see what it happens, what it does to the suction and blowing. Okay. Now, following our old similarity transformation, okay, we can write something like this here, where this is nothing but the stream function. Okay. The significance of this, and neta is of course the same as the similarity variable what we had earlier. Okay. So, v, that means the velocity, the vertical component of the velocity becomes something like this. Okay. So as you know that V is nothing but the differential of psi with respect to x, right, psi being the stream function. Okay. This is once again nothing like it is exactly the similarity solution that what we did earlier. Okay. But V now is equal to V naught, right, at y equal to 0, which means at neta equal to 0, right. Okay. So V naught will be given by u infinity gamma x into m plus 1 by 2 minus f evaluated at 0, right. Okay. So V naught is also once again just writing it in a proper way, f0, that means f evaluated at 0, right. Okay. Then x raised to the power of m minus 1 by 2, okay, multiplied by gamma. Okay. So this is the form that we have in this particular case. We also know that f naught is not a function of x. Okay. So f naught is not a function of x, that part we know. Okay. Therefore, if this is not a function of x, then you can imagine this is the left hand side, this is the right hand side of the two equation, right. So if f naught is not a function of x, then let us write f naught, take everything to the other side, is basically v naught 2 by m plus 1 by gamma c 1 plus x m minus 1 by 2. Okay. So this is not a function of x, that means we can say it is not a function of gx, right. So obviously in order for this to be true, that f naught is not a function of x, you can imagine that your v naught has to vary as x to the power of m minus 1 by 2, right, because then only this and this will cancel each other, right. Okay. So if it does not vary by this particular way, then you will have an x dependence. F naught will be a function of f in that particular case, if this is not true. Got it? If this is not true, that is what is going to happen. So if that happens, the entire similarity solution actually breaks down. Okay. So for the similarity solution to be applicable for the general case of suction and blowing, okay, what we are going to have is that your f naught cannot be a function of x, that is a given, okay, and therefore your v naught has to vary in the same way as x to the power of m minus 1 by 2, which if m is equal to 0, that means it is a flat plate basically, right, with no angle, right. So v naught in that particular case should vary as x to the power of minus half, right, for similarity solution to hold. Right. So that means, okay, as your distance x increases, right, it's 1 over inverse, right. So it's basically comes down in this particular fashion, correct. That is how it is coming down, okay. And as you know that the boundary layer grows up by x to the power of half, right. So the boundary layer as it progresses, this actually decays. Whether it is moving up or coming down, that depends, right. It is like whether it is a porous matrix or it is like a perspiration, okay. So for this to hold, the similarity solution to hold, you have v naught which should vary as x to the power of minus half, okay. Now this m, once again we have not said about the nature of m except that it is equal to 0 for beta equal to 0, that means when the wedge becomes a flat plate. Now m equal to 1 corresponds to a stagnation flow, that means it is a flow somewhat like this. In other words, it is also called the Hyman's flow, okay. So that is equal to m equal to 1. Once again we will come across what these quantities are, right. So in that case v naught should vary as x to the power of 0, okay, that is it is x independent. Got it? It's x independent. Got it? So, this is x independent for the Hyman's flow, it is x to the power of minus half for a flat plate, and for in between any other parameters or any other angles, okay, it should vary as x to the power of minus m minus 1 by 2, right, in order for the similarity solution to hold. Now, remember, you can have any type of suction and blowing, right. For these kind of parameters, if the functional form is like this, then only the similarity solution will hold. Okay. But in real life, you can have other kinds of suction and blowing as well. Okay. So, in this particular vein, let us define a parameter called f naught, which is 2 by m plus 1 v naught by u infinity, Reynolds number of half. Okay. This particular parameter space is called the blowing parameter. Okay. It affects the boundary layer thickness, of course it does, okay, and the shear, obviously, because if the boundary layer thickness changes, the angles will change, so naturally the shear will change, right. So, in this particular way, this f naught parameter, this part is called the blowing parameter. Remember this, v naught by u naught into Reynolds number based on x raised to the power of half. Now, how does suction and blowing actually play a role? So, physically, intuitively. So, if there is a, say, a blowing happening like this, okay, what do you expect? Initially, the boundary layer, say, is something like this, right. With suction and blowing, when you actually pump in momentum in that upward direction, the boundary layer is supposed to go like that, right. So, there is a displacement of the boundary layer in the upward direction, right. So, in other words, the slope, if this was the slope for the boundary layer after it was kind of blown outward, this slope over here will be much more, you know, much more higher in that way, because the boundary layer thickness is now lower in this particular, at the same location. If you talk about location to location, at the same location, before blowing the boundary layer thickness was delta, after blowing it, say, it's delta prime. So, obviously delta prime is more than delta. Similarly, when you actually have suction, that means when you have it in the opposite direction, the boundary layer becomes thinner. Okay. So, the gradients actually gets enhanced. Okay. So, the gradients will get enhanced. So, this actually proves that why we are going to get a change in shear and obviously a change in boundary layer. Okay. So, let us look at the energy transport. What does it do to the energy transport? So, here we have easily explained that if delta changes, okay, obviously you know that the CF, or basically the drag, is dependent on delta. Okay. So, naturally as delta changes, that also changes. Okay. So, the energy transport, okay, if you recall the energy transport that we did earlier, this is, I am just adding a term called m plus 1 in this particular case. We will come to the significance of m plus 1 once again when we do the suction, when we do the Faulkner scan class of solution. Once again, assume that this is the energy transport. Okay, let's assume it in this particular way. So, this is that. Let us do a little bit of mathematical jugglery on this, or okay, or theta neta okay, straightforward integration. Now, theta infinity is equal to 1 we all know that. I am not going through the steps once again. Theta 0, theta prime 0, 0 to infinity, okay. So therefore theta neta, that means the total function, okay. Okay. So this is the total expression that we actually get for theta neta. Okay. Now for a wedge we will see how this actually varies, but it is already incorporated in that m plus 1, right. Now if we look at therefore the solution, that how this is going to really look like, okay, when you actually have suction and blowing, let us look at the PPT where we will show that how that thing actually happens. So okay, let us look at first that how the boundary layer is going to change, okay, using quantitative information. What I did was draw qualitatively, okay, what is going to happen. Now if you look at the annotations that I have actually made, if you recall that your V is a function of u infinity into delta by x, isn't that so, right, okay, and delta is obviously x into Reynolds number minus x to the power of half, right, okay. So V naught was actually equal to u infinity into Reynolds number to the power of minus half, right. So these are the 4 scales that I have written on the top of this particular thing, right, okay, because the first scale comes from the fact that dV by dy is the same as du by dx, right, because that is the continuity scale that we have, okay. Now what we have done is therefore we have plotted this blowing parameter which we already defined in our previous class, okay, and f double prime 0 is nothing but the slope, okay, or the corresponding shear, you can talk about it as a shear, okay. So you have basically 2 series, one is blowing parameter and one is the suction parameter. So this part which is the positive side is basically blowing, and this part which is the negative side is basically suction, right. So this part is positive, this part is negative, right. So as you can see that when you continuously go on blowing more and more, that means you are increasing the blowing parameter, right. If you recall what the blowing parameter was, we just did it, let me write it down over here so that there is no confusion, okay, x to the power of half, right. So that was the blowing parameter, right. And as you can see the order is also, we have just proven the order over here. This is like V naught scales as u infinity into delta into Reynolds number to the power of minus half, that means they are of the same order. So that is why you see the numbers are also of the same order, right, they are all about 1, of the order 1, that is what exactly what we have done over here. So what you see, as you increase the blowing, as I said that the boundary layer is blown outward, right. So therefore there is a sharp decay in the shear, because here if you look at it, so this is the shear that you found normally for a flat plate. So the middle one is an impervious flat plate, right. So as you can see over here that there is a lot of blowing, okay, and because of that there is a sharp decay in the shear stress, right. Whereas when you actually have suction, that means the boundary layer should become thinner, okay, you see over here that there is a sharp increase, okay, almost from about 0.3, right, all the way to about close to 2.7, right. So it's roughly a 1 order increase, okay, in the shear stress. So, there is a very high shear level when you actually have suction at the wall, right. And the blowing parameter is always, remember, of the order 1, comes from this particular scaling and from our definition. Now, let us look at, okay, in the suction side we went up to this, okay, whereas on the blowing side we found that it becomes equal to 0 very fast, right. Do you see that? It becomes 0 right after we cross about 0.5. So, around 0.6, 0.7 it becomes equal to 0. Okay, why that is the case? Okay, that is because as you blow the boundary layer more and more, this is how the boundary layer is increasing as you increasing the blowing, right. After you increase it beyond a certain amount, the flow starts to separate. Okay, the flow starts to separate, not exactly like that, but say you have increased it to the limit that it has reached the, so here the flow will actually separate. Okay, because the gradient is slowly becoming shallower and shallower. If you look at my hand, it becomes slowly shallower and shallower and shallower till at a point when it becomes equal to 0, and after that there should be actually what we call a separation. Okay, so the flow actually separates beyond a certain point because the gradient, the slopes will become like this. So, this is the original one, this will be the one after some time, this will be after some time, this will be after some time. So, at one point of time this particular point will actually separate. So, that is the reason why blowing, you cannot go to high levels of blowing because you will separate the boundary layer, right. Whereas, on the suction side you can go very high because it is a favorable kind of a phenomena. So, that you are compressing the boundary layer in such a way that your shear goes on and on and on, it increases more and more, there is no separation effect as such. Okay. So, that is an interesting thing. Okay. Now, the blowing parameter, let us look at it in terms of the, the heat transfer, okay, because the heat transfer is the other half of the story that we have, okay, for which we said that what will be the theta, okay, we derived the theta. So, if you look at it here, it is Nusselt number, okay, divided by Reynolds number to the power of 0.5, right. So, because that is the Reynolds number scaling is always half, okay, and we have different Prandtl number families after that. So, this is once again the blowing parameter space, okay. So, once again you have this point at 0, right, which is basically the flat plate, impervious flat plate. This part is basically blowing, this part is once again suction. Once again the same thing, what will happen when, as you know that when you make the boundary layer smaller, okay, that means you make delta go down, delta T obviously also goes down, right, delta T also goes down, the thermal boundary layer also goes down, correct. Okay. Similarly, when you make this go up, okay, delta goes up, delta T also goes up, right. So, it actually has a very similar kind of connotation, right. So, in this case what you see is that basically your Nusselt number by Reynolds number scaling, it goes to 0, right about the same time when your separation actually happens, right, because separation means you lose the boundary layer altogether, whereas it goes upward, that means you have an enhanced heat transfer because of the lowering of delta T, because if you recall H is proportional to 1 over delta T. So, as delta T goes down up or goes down, H actually goes up. So, therefore, you have a sharp increase. Okay. So, this is a very similar trend as F double prime 0, right, very similar trend as your shear, except for the fact now with Prandtl number dependency you have different types of variations. Okay. The curves do not actually fall on the top of each other, okay, they are actually a little bit spread out. So, that is what you see over here, the curves are a little bit spread out, okay, and you see that for Prandtl number, as you go on changing the Prandtl number, the slope of these lines actually change, okay. But however, they seem to merge, okay, beyond for all the blowing cases, okay, but whereas for the suction cases there is a little bit of difference, that means there is a little bit of branching out of this particular curve, but otherwise they are very similar to your F double prime. Okay. So, what suction and blowing does is that, in a nutshell, when you do blowing you actually increase the boundary layer thickness both for thermal as well as for momentum boundary layer. As a result, you reduce the heat transfer coefficient and you reduce the shear stress. Okay. Whereas on the other side, if you go to the suction side of things, okay, what happens is that you are reducing the as you go on increasing the or decreasing the blowing parameter, or that means you are increasing the level of suction, your boundary layer thickness becomes very short. As the boundary layer thickness becomes very short, both your wall shear stress, that means your basically your drag, as well as your heat transfer coefficient, both shoots up. These are the things that you must take out from this particular piece of argument, and this is the happens because suction makes the boundary layer smaller, whereas blowing blows the boundary layer off. Now this is valid for all types, not just for flat plate, it is also valid for wedges of any particular angle. But for the similarity solution to hold, we already know that it has to vary in a certain way. Okay, this suction parameter has to vary, or the blowing parameter has to vary in a certain way. That means V naught has to vary in a certain way, which is basically given by x to the power of m minus 1 by 2. Okay. So once those things are obeyed, this is the nature of the graphs that you have. Okay. So in the next class we are going to look at the wedge.